So I consider what the exercises that we're going to go over in this video to be tying up loose ends from last week. All right, so nothing that I'm doing in this video is brand new, but it's taking some of the skills that we reviewed last week with fractions and other rational expressions and extending it to some more challenging problems. So I gave you homework for tonight on page 70 in the textbook. So I'm doing a few. This is number 44 off of page 70. And we reviewed operations with fractions. I think almost everybody got that perfect on their quiz where you had to add two fractions on the quiz. Now this is a little bit more complicated, but it's the same concept. Okay, so we need a common denominator. Now these have no common factors, right? Because x is not a common factor. It's part of a sum or a difference. So if there's no common factors and we need a common denominator, then the common denominator ends up being simply the product of the two denominators. Okay, now when we get a common denominator, in order to combine these two expressions, we get the common denominator and we multiply in order to change the appearance but not change the value, right? We multiply each fraction by 1. And x plus 6 over x plus 6 has the value of 1. Okay, so I multiply the first fraction by x plus 6 over x plus 6. And you probably never realized all those years that you were adding fractions and getting a common denominator, you probably never really even realized that the reason it's legal, you know, what we do when we get a common denominator where we multiply the top and bottom by the same thing, we're just multiplying by 1. All right, and that's how we know that we keep the value of the fraction the same, but we change its appearance. Okay, so we get to here. So when I combine these two, let's see, this numerator is going to have a result of, if I distribute, x squared plus 6x. And one error that I'm seeing like crazy in class is students not distributing the negative, right? If I am subtracting this quantity, right? So right now, if I just distribute, this is 3x plus 12, but because I am subtracting, right, and I am subtracting a quantity, I might want to put this in parentheses so that I remember to distribute my negative all the way through. Okay, and then I'd get x squared plus 6x, and then distribute that negative. So I've seen that over and over as I've been helping students in class, people not distributing the negative, right, and changing the signs. All right, and so then obviously those middle terms can combine to 3x. And let's see, could I do any more simplification, right? Because I do have a quadratic here. Could I find factors of 12, negative 12, that add up to positive 3, right? 1 and 12 are not going to do it. Neither is 2 and 6. Neither is 3 and 4. So it looks like I can't simplify that any further. And whether you leave the denominator as x minus 4, x plus 6, or whether you replace that with x squared plus 2x minus 24, because the numerator won't factor, right? You know, whether you leave the denominator in factored form or multiply it out, you know, I am totally fine either way. And students often ask me, well, how do you want me to do that on a quiz? If it's equivalent, it's equivalent. Any equivalent form gets you the full credit on a quiz or a test. So we also know that when we multiply fractions, like let me give you a nice easy example of multiplying fractions. We know we can multiply across the top and across the bottom, right? That's how we multiply fractions. We don't get a common denominator when we're multiplying, and this would be 18 over 36. I could simplify 18 over 36, right? 18 goes into 36 twice, right? So this actually simplifies to a half. All right, but we know that we could simplify it all at the end, or we could simplify by canceling on the diagonals. All right, that's something that only works if there's a time sign in the middle, right, for a product. But I could say 2 goes into 2 once, 2 goes into 12 6 times, and then I could say 3 goes into 3 once, 3 goes into 9 3 times. Then when I multiply across the top, across the bottom, I get 3 over 6, which is a half. Okay, so it's nice to simplify first before you multiply. And so that's what I'm going to suggest you do here. And so on this whole entire page of exercises, I think it's going to be great practice with factoring. Right, I mentioned in class that I hope all of you are good with this type of factoring of quadratics. Again, when a is 1, right, it's so much easier to factor, right, when the a is 1. So I need factors of -3 that add up to +2. That means I want the positive on the 3. This is pretty easy to factor, right? There's only one possibility for factors of 3, right? 3 and 1. But this time I want to add them up and get a -2, which means I need to have the positive on the 1. And then I want to cancel as much as possible. I can't cancel. Oh gosh, wait a minute. I thought I did something wrong because I knew this was supposed to work out differently. So bear with me a second here. This should be minus. There we go. I knew there was other stuff that's supposed to cancel. So notice, and remember, we're trying to not say cancel, we're trying to say divides to 1. So x plus 3, 3 plus x, that divides to 1. Now, when we ran into this the other day in class on one of the exercises we were doing with the complex fraction. If I have 3 minus x, and I want to divide by x minus 3, they're not exactly the same, right? The signs are switched. And so what I was telling students in class who were having trouble with, how does that cancel if the signs are switched? And I said, well, do these problems for me, right? What's 3 minus 2 over 2 minus 3? Right? That's 1 over -1, okay? How about this, right? That's 2 over -2, right? Which would result in, when I simplify, -1. So anytime I have factors that look almost identical, but the order's switched for subtraction, I mean, it doesn't matter for addition, right? But if I switch the order for subtraction, I can divide these and get a -1. Okay, so now what I'm left with is -1 times x minus 1 in the numerator. And then I am left with, in the denominator, x plus 1. And I'm okay with you leaving the answer like this. I'm also okay with you going like this and distributing. Sometimes students come here and they try to cancel, right? They say, well, can't I cross those ones out? Or couldn't I cancel these, and get -1? But remember, these are part of a sum, right? And so I hope we're becoming experts on that. We cannot cancel terms out of a sum, right? We can only cancel when we have a product, right? That's why canceling was legal up here, right? Is I have a product. So if I have a product, I can cancel factors out of a product, okay? But I can't cancel something out of a sum. So this, either form, would be my correct simplified answer. Now, moving on, I had these prerequisite skills up in a previous lesson, but they're worth looking at again because we're going to need the same skill here. So unless you very quickly can get the answer right in your head, you should be able to. Another way you could think of this, also, we know powers of the same base, we add the exponents. Another way we could think of this is x to the half times x to the half, add the exponents. Well, what's a half plus a half, right? It's a whole. X to the first, which we don't write x to the first, we just write x. Okay, and so anytime we multiply a radical by itself, right, we square a radical, which, you know, that undoes, those operations undo each other. Or again, you know, I could think of it, and I'm highlighting this school of thought because we're going to use something like this when we get down to the next example. I could think of it like this, and I hope you can fluently switch between radical something or that expression to the half power. All right, so the square root of some quantity is the same as raising the quantity to the half power. You'll want to, in these next two exercises, be able to fluently switch back and forth between those representations. But again, add exponents, powers of the same base. I can add the exponents, and that's how I get x plus 1 to the first, which I don't have to write to the first. Okay, so this is actually number 7 from the worksheet that we were doing last week. Okay, and there's many times when I was teaching Calc 1 where students would end up with something here on the left, and they'd flip to the answers in the back of the book, and the answer key would say this expression on the right. Okay, and students would be very upset and say, I don't know what I'm doing wrong. You know, why did I get this? And the answer key says this. And these look very different, but they're actually equivalent. And so I want you to work through this exercise and show why these two are equivalent. So this boils down to just simplifying a complex fraction. Okay, the only denominator in the problem, right, is radical x. Okay, so we learned last week that when I have a complex fraction, the best way to approach that is to multiply by 1, right, in the form of the denominator, the least common denominator over the least common denominator. Okay, so, oops, wait, I meant to put parentheses there because I'm going to take this and I am going to distribute it in to each term. Okay, and so then when I do that, okay, so here I recopied it here because I didn't want to have to multiply again. So I'm multiplying by radical x here, multiplying by radical x here, and down here I want to note that I have radical x times radical x, 2 radical x, times 2 radical, and then times another radical x, right? Because I had to square this. All right, so let's take a look at what we've got here. Radical x times radical x, that was in prerequisite skills, so that's just x, right? So I'd have 10x. Then over here, these divide to 1, and then this is so important. I'm seeing this mistake over and over again. So many students just say, okay, 5x plus 1. Think about that for a second and try to tell me what's wrong with what I just wrote. Okay, because I am left with 5x plus 1. What's wrong with how I wrote it like this? Okay, and it wouldn't matter if this was a plus sign. If I had a plus sign here, this would be fine. What I have to really focus on is that if I have subtraction, I have to use parentheses. I have to distribute that negative through that entire numerator. All right, then in the denominator, I have 2 plus 2, 2 times 2, which is 4. And then maybe I think of x, instead of radical x, how about I think of it as x to the half? And then I have x to the half times x to the half times x to the half, or in other words, x to the half cubed. So I could either think of multiplying, right? Because if we have this situation, we multiply the exponents. Or if I have powers of the same base, half plus a half plus a half, right, for exponents. So this gets me x to the 3/2. Oh, sorry, that's a very sloppy 3 there. But anyway, when I distribute through parentheses, and I would get 5x minus 1, and then 4x to the 3/2. So the next problem I took from, this is actually one of the things I assigned you in homework, number 81. This is part of tonight's homework. But I wanted to start this with you because students often do a couple things incorrectly here. The first thing that students do incorrectly is they see the negative exponent, and I encourage you on all of the homework exercises, when you have a negative exponent, bring it downstairs. Students typically try to take this and bring it downstairs like this. And again, I want you to fluently work between, writing it as a radical or writing it to the half power. So they bring it downstairs next to the x plus 1. However, that would also put this in the denominator of this expression. Okay? If I didn't even have a numerator, right? Or a denominator, sorry. If I didn't even have a denominator, and I said, write this expression with negative exponents, I hope you'd realize that the first part kind of stands alone, right? The first term in this difference stands alone, and then you would bring this just in downstairs under the x, right? Because it's only being multiplied by the x. So I hope this representation helps you see why the x plus 1 doesn't come down here, the radical x plus 1. The radical x plus 1 is only underneath the x. Okay, so again, we have a complex fraction, a fraction within a fraction, and we only have one denominator, right? That denominator is 1 plus radical x. So I'm going to let you do most of this work because it is part of your homework. The one part that I want to help you with, though, is when you get to the answer key and you go to check your work in the answer key, you're going to see a denominator of x plus 1 to the 3/2. And you're probably going to say, how did they get that? Okay, because probably you are going to leave your denominator just written like this. Okay, and I know when I'm teaching Calc 1, like I give this full credit on a test or a quiz if students write their answer like this. Okay, so most of you will probably write this for the denominator. That's not the final answer, just the denominator. However, this is not in simplest form, right? Because first of all, 1 plus x, x plus 1. So, I can use those interchangeably. But remember, this first quantity is x plus 1 to the first power. And this second quantity is x plus 1 to the half power. And when I have powers of the same base, right, I add the exponents. And so maybe now you're starting to see on that one fraction exercise where you had a whole section where you were just adding 1 to a fraction, you're probably starting to see how that comes up so often, right? So if I added 1, and we don't want to write to the 1.5 power, we want to leave it as an improper fraction. So x plus 1 to the 3/2, that will be the denominator. So I'll let you finish the rest of that exercise on your own.